Hi everybody, in this video we're going to talk about combining probabilities. We recall we're going to be dealing with theoretical probabilities on all of this, and so of course we talked about subjective and we talked about relative frequency, but now we're going to be looking at, well, what should happen? But we're going to be looking at of more than one event occurring. So we're going to be combining things, and of course we know that excuse me, combining events, we're either going to combine events with the words and or. So we're going to look at the and. So we're going to be looking at the probability of first of the way A and B can occur, which is the probability that both of those events occur. Okay. These events can be either independent or dependent. And that's how we're going to split this up, and we're going to be looking at those in terms of independent events and dependent events. And we're going to start with the independent events because that's probably what we've been working with before, is working with single events. They are independent. Okay. Two events are independent if the outcome of one event does not affect the probability of the other event. Okay, now here's what that means. That means like when you're flipping a coin. If you flip a coin one time, then of course that's independent. But then if you pick that same coin up and flip it again, the next time it occurs, that is also independent. So what happens on the first roll has nothing to do with what happened on the second roll. Okay. So if they are event, the probability either if A and B, the probability of A and B occurring is you take the probability of A and multiply it times the probability of B. And this can be extended if you're looking at 3 events or 5 events or 10 events, if you're flipping a coin 10 times or you're rolling a die 15 times. Every time you roll it, it is an independent event, and however many there are, that's how many you are going to include in this. Okay, so here's the formula that you need for that if they are independent events. Okay, all right, so that's the formula we're going to be using. We're going to start talking about something that we did in our last lesson, which is rolling 2 dice simultaneously. Okay, so, and we are going to look at the first die can land on a 1, 2, 3, 4, 5, 6. The second die can also land on a 1, 2, 3, 4, 5, or 6. And there were 36 possible outcomes. Combinations of the numbers. You could get a 1 and a 1, or a 2 on the first die and a 5 on the second, or whatever. Okay, why are these events independent? Okay, well, they are independent because the roll of the first die does not affect that's an E, affect the second die of the second. They are independent events. It doesn't matter what you roll on the first, it has no impact on what happens on the second. Okay, so let's look at this by looking at our table and visualizing, and we're going to show that the formula actually does work based on something that we can figure out. Okay, so on the diagram, we want to mark where both die land on a 5. Okay. Well, if we do that, then we're looking for the place where we have a 5 and another 5. And that, of course, only occurs once in this one space. Okay. So the probability of this, we know that there is 1 square out of the 36. So the probability of getting a 5 on the first and a 5 on the second is 1 out of 36. Okay, so let's verify that using the formula. Okay, so let's look at the probability of a 5 and a 5 can be broken down into the probability that the first lands on a 5. Okay, so where the first die lands on a 5 is this, which gives us there are 6 of these out of the 36 possible combinations. Okay. Now, the probability that the second die lands on a 5, an independent event, is all of these where the second die is a 5. So there are 6 of those out of the 36 possible. Now, of course, however you want to multiply fractions is fine. What I always do is I try to reduce it as much as I can. I know 6 goes into 36 6 times. 6 goes into 36 6 times. This really becomes 1 times 1 divided by 6 times 6, which is 1 out of 36. And notice that these two are the same. Okay, so let's look at the probability of multiple events. Okay, person A and person B both flip a coin 5 times. Person A lands on 5 heads in a row, and person B is a head, tail, tail, head, tail. Why are these events independent? Okay, well, the flip of a coin is not affected by a prior flip of the coin. Okay, so the fact that I got a heads on the first one has nothing to do with the second, the third, the fourth, the fifth. Same thing here. The outcome of the second flip has nothing to do with the first. The third has nothing to do with either of those. Okay, so we know that these are independent. So if I want the probability of 5 heads in the row, then really what that means is head and head and head and head and head, which means this is the probability of a head times 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 the probability of a head. Now, we know from prior experiments that the probability of head, remember on each, you can either have a head or a tail on each roll or on each flip. Okay. So the probability of a head is 1/2 times 1/2 times 1/2 times 1/2 times 1/2, and if we multiply those numerators, 1 times itself any number of times is 1. 2 times 2 times 2 times 2 times 2 is 2. Now let's look at the person B. Well, this would be the probability of a head times the probability of a tail times the probability of a tail times the probability of a head times the probability of a tail. And again, you can either get a head or a tail on each flip, so the probability of a head is there's one way out of the two outcomes. The same with the tail. There's only one way to get a tail out of the two possible outcomes. There is one way out of two, one way out of two. For either the head or the tail, oops, and this is 1 out of 32, excuse me. So this is 1 out of 32. Notice that these are the same. And we're going to talk about that in just a minute. I know when we were in class, we asked, well, which one do you think is more likely to happen? And almost everybody, including me just at first blush, would say, well, this one. Because they're not going to get ahead 5 times in a row. Well, let's extend this. What is the probability that they flip a tail on the 6th flip? Well, it's 1/2. On the 6th flip, you can get a head or a tail, so it's 1/2. The same thing is going to happen for person B is 1/2. This brings us to what is called the gambler's fallacy. And it is the mistaken belief that a streak of bad luck means that you're due. This would be like if somebody had bet on tails and they had heads 5 times in a row, they would say, okay, I've had 5 heads in a row, so the next one has to be a tail. Well, it doesn't matter. They're independent events. But this is how gamblers can get into trouble. They think, okay, well, I've lost 5 hands in a row. I'm bound to win the next one. Or if they're in playing roulette, well, it's landed on black 8 times in a row, so the next time it has to land on red. Or whatever the situation is. But each of those events are independent, and what has happened before does not mean that it's have any effect on what's going to happen the next time. Okay, now to show you before we actually get into how to calculate dependent probability, we're going to look at what is the difference between independent and dependent events. Okay, so we're going to do 2 experiments. We are going to, in a bag, we are going to put 2 blue and 2 yellow. Okay. Then we are going to randomly draw a tile from the bag. Okay, now the difference comes with what do we do with that tile after we've drawn it. Okay, are we going to, because at that time we have 2 options. We can put it back in the bag or we can keep it out of the bag. Okay, so our first draw, we have 4 tiles in the bag. And you know your choices of drawing out of there are either a blue or a yellow. Well, the probability of a blue, there are 2 blues out of 4 possible combinations, or 4 possible outcomes. And the probability of a yellow, well, it's the same thing. There are 2 yellows out of the 4 total tiles. Okay, so that's the probability for the first draw. Okay, now in this one, I have put the tile back in there. So now I'm done with this. It's completely independent. I can cover it up. What happened here has nothing to do with what's going to happen on the second draw. So when I put it back in, my bag is exactly the same. So I still am going to be drawing from 2 blue and 2 yellow. So the probability of a blue on the second draw is still 2 out of 4. The probability of a yellow is still, there are 2 yellow out of the 4 tiles. Same thing here, whether I drew a blue or a yellow the first time has nothing to do with it. So the probability of a blue is still 2 out of 4, and the probability of a yellow is still 2 out of 4. Okay. So now I can look at the outcome is the probability of the first draw times the probability of a second. And the 4 combinations are a blue-blue, blue-yellow, yellow-blue, yellow-yellow. So the probability of a blue and then another blue is 2 out of 4 times 2 out of 4, which gives me 4 out of 16. The probability of a blue-yellow is 2 out of 4 times 2 out of 4, which still gives me 4 out of 16. The probability of a yellow-blue is 2 out of 4 for the first one of yellow, 2 out of 4 for the second, and I get 4 out of 16. Then lastly, the probability of a yellow yellow is the probability of a yellow times the probability of a yellow, which is also 4 out of 16. Okay. Now you will see that by replacing the marble, so this is with replacement, these are independent events. Now, why is that the case? If the tile from the first draw is replaced, it has no impact or no effect on the draw of the second tile. Because the tiles in the bag don't change. Okay, so replacing the first tile means that nothing changes. But let's say we don't replace the first tile. Okay, so we're going to do our first draw. We've already done this. We've got 2 blue and 2 yellow. So the probability of a blue on the first one is 2 out of 4. The probability of a yellow is 2 out of 4. But now notice here, that the first tile is not replaced. So that means the bag changes. So it does, whatever happened on the first draw does impact the second one. Okay, so on the first draw, if we drew a blue and we go to our next one, that means there's only 1 blue and 2 yellows in there. So when we draw on the second one, the probability of a blue, there's only 1 blue out of the 3 tiles. The probability of a yellow, well, there are 2 yellows out of the 3 remaining tiles. All right, so now let's look at it in the situation where the first one was a yellow. Okay. Well, if the first one was a yellow, then the only thing, and I do not replace it, then the only thing left in the bag are the 2 blues and the 1 yellow that was not chosen. So the probability of a blue is now 2 out of 3, and the probability of a yellow, there's only 1 yellow out of the 3 remaining. So now we calculate our probabilities exactly like we did before. The probability on the first draw for a blue is 2 out of 4. On the second draw is 1 out of 3, which gives us 2 out of 12. The probability of a blue and a yellow, well, 2 out of 4 for the first draw, but notice the probability in our second draw has changed to 2 over 3. So that gives us 4 out of 12. The probability of a yellow and then a blue is 2 out of the 4 on the first draw, and then 2 out of 3 on the second draw, which gives us 4 out of 12. And then finally a yellow followed by another yellow is 2 out of 4 times 1 over 3, which is 2 out of 12. So drawing 2 tiles without replacement is an example of dependent events. And so what does that mean? That means that the first draw does affect the second draw. The probability for the second draw. Because the bag changed. Okay. All right, so let's go back to the first page now and talk just for a minute. Let's go ahead and define dependent events. So two events are dependent if the outcome of one affects the probability of the other. So two dependent events follow this formula. The probability of A and B, if they are dependent events, is the probability of A times the probability of B given A. Okay. So the probability of B given A. Okay. If they're independent, it doesn't matter what happens on the first one. But if they're dependent, you have to say, okay, well, because this happened in the first draw, this is the probability for the second one. So we'll keep that formula in mind, and let's do a couple of examples with dependent events. Okay. All right, so we've done some work with drawing a card. If we're having a standard deck of 52 cards. If we draw a card, place it on the table, and then draw another card. So we're going to take a card, we're going to place it on the table. That means without replacement. Okay. So we started out with 52 cards on the first draw, but on the second draw, we're not putting whatever that card was back in, so we're only dealing with 51. Okay. So why are these events dependent? Since the first draw is not replaced, the deck changes to 51 cards, which affects the probability of the second draw. Okay. Okay, so let's see, what is the probability of drawing 2 kings in a row? Okay, well, let's think about what that means. Well, this is the probability of a king and a king. I guess I should have abbreviated both. But since they are dependent, I'm going to have to find the probability of a king times the probability of a king given a king on the first draw. Okay, so On the first draw, the probability of king, well, we know there are 52 cards and there are 4 kings. Now on our second card draw, there are only 51 cards remaining because we've taken out a card and that card was a king. So there are only 3 kings remaining. Okay. So on this draw, you can say there are 3 kings remaining in 51 cards. So now when I do this, and I know I've said this in class, I don't care if you reduce these fractions or not. They can be reduced, I don't care. So if I'm going to find this, I'm going to multiply 4 times 3, which is 12. 52 times 51 is 2,652. So this is the probability of drawing 2 kings in a row. 4 kings out of the original 52 cards. There are 3 kings remaining out of the total of 51. Now, a visual on this can be really helpful. So on our first draw, we know that we have 4 kings out of the 52. But then one of them is chosen. So that means that this card is gone. It's been eliminated. So for our second draw, there are 3 kings left out of a total of 51 cards. Okay. All right, well, let's try to relate this to something a little bit different, and this is something that we really don't have like a picture of a deck of cards. Consider the following situation. You are selecting people to serve on a 3-person committee from a pool of 10 women and 10 men. Why are these dependent? If a person is chosen, they are removed from the pool. So it affects the other probabilities. Okay, now I'm very visual, you know that. So just to, and as we're working on this, so what is the probability of selecting an all-male 3-person committee? Okay. So we're actually looking at the probability of a man, and a man. Okay, well, here's what I'm going to do. Just to give myself a visual, I am going to draw my committee over here, or my selection. I've got 10 men and 10 women. So let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 men. Not very creative. Use blue for men and pink for women. W, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. All right, now in terms of the probabilities, let's start out with the probability of a man. Okay, so we're going to start with the probability of a man. Okay. And we know that there are 10 men out of the 20 choices. Okay. All right, so once I have selected a man, he is out of the pool. So now I have to find the probability of a man given a man on the first one. Okay. Well, there are no longer 20 to choose from. There are 19, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9 men. Okay. So now another one is on the committee, and these are the people being chosen. Okay. So we're going to find the probability of a man given 2 men have already been chosen. Well, now there are only 18 candidates remaining, and only 8 of those are men. And if we do the multiplication on that, this becomes 720 over 6,840. Okay. All right, on the next page, we're just going to practice some more. All right, so let's see here what we've got. We have a bag of M&Ms. There are 6 red, 5 yellow, 2 green, 1 blue, and 4 purple. And yes, I do know that there are no purple M&Ms, but it's the color of pen that I had. Okay. All right, now to entertain myself, I'm going to do this. Okay, so I've got 6 red, so I'm going to draw 6 red. I've got 5 yellow. I've got 2 green. I've got 1 blue. And I have 4 purple. Okay, so those are my M&Ms. And there are a total of, if I count these up, 6, 11, 12, 13, 14, there are 18 total in the bag, in the original bag. Okay, all right, so now I have a visual. I can kind of deal with whatever I'm thrown at. You select an M&M from the bag, eat it, and select another. If you eat it, this means without replacement. Which means these are dependent events. Okay. Since you are not replacing, the first M&M, it affects the probability of the second draw. Okay. Okay, so what is the probability of drawing a red followed by a green? So what we're looking for actually here is the probability of a red and then a green. Which is the same thing as saying the probability of a red times the probability of a green given the red. Okay. So the probability of the red, we know on our first draw there are 18 total M&Ms, and there are 1, 2, 3, 4, 5, 6 red. Now, I'm not going to be able to cover these up unless I want to redraw it, and I don't want to do that. But I know that one of these is gone. So the probability of a green, there are 2 green out of the remaining 17 M&Ms. So when I multiply this out, this gives me 12 out of 306. Now, if your calculator automatically reduces, this is 2 out of 51. But this is perfectly satisfactory. Okay. All right, what is the probability of drawing 2 yellows? Okay, so what I'm really looking for is the probability of a yellow followed by a yellow. So this is the probability of a yellow times the probability of a yellow given that I've already taken a yellow. Okay, well the probability of a yellow, we know in the original bag there are 18 and there are 5 yellows out of that. But for my second draw, one of the yellows is gone, which means there are only 17 M&Ms in the bag and there are 4 reds. So that gives me 20 out of 306, or 10 over 153. And again, this is perfectly satisfactory. Okay, so the next one is, what is the probability of 2 blues? Well, that's really asking me the probability of a blue and then another blue. Okay, so that's going to be the probability of a blue times the probability of a blue given that I've already taken a blue. Okay, well the probability of a blue, I know I'm back to my original 18 M&Ms, and there's 1. Okay, so it's gone now. So now the probability of getting another blue is 0. There are none left out of the 17 remaining, which is 0 over 306, which is 0. Now remember, a probability of 0 means it is not possible. Oh, my blue pooped. I hate it when that happens. This is impossible. And that is what a probability of 0 means. Okay. Now, just like we said earlier, this can be extended to more than 2 events. Okay, so let's see, what is the probability of drawing a red, then a blue, and then a purple? Okay, so this is the probability of a red, a blue, and a purple. Okay, so let's start out with, this is going to start out with the probability of a red. Okay, well we're back to our original bag, so we have 6 out of 18. Okay. 1 is gone. So now we've got the probability of a blue given that we already have a red. Well, I know there are only 17 M&Ms left, and there is 1 blue. Okay. So now, and I'm going to go ahead and mark these off since this is our last one. So I've gotten rid of the red, I've gotten rid of the blue. So now I have to find the probability of a purple given red and blue. Well, now I've got 2 out of the bag, so there are only 16 left, and there are 4 of those are purple. So if you multiply that out, you get 24 divided by 4896, which I think reduces to 1 over 204, but I'm not sure about that. Okay, but again, this is perfectly okay. Okay, all right, so remember when we talked about the different probabilities for the outcome of a family with 3 children? Okay, there are 8 equally likely combinations. The girls, 2 girls and a boy, and so on and so forth. Okay, so using this list, what is the probability that all 3 children are boys? Okay, well there's only 1 of those. So the probability of BBB is 1 over 8. Now this is kind of how the multiplication principle works, but let's see using the formula if the probability of BBB gives a boy and a boy and a boy. Well, the probability that the first child is a boy, it's either a boy or a girl, so that's 1/2. The second child is 1/2. And finally, the third child is 1/2. And this is also 1/8. And we know, of course, that these are independent because what happens on the second one has nothing to do with what happened on the first one. Okay, time to change videos.